Attendance. Okay, I hope everyone's doing fine. At this point, recording's turned on, so you can type in your name, and we'll have your record for attendance. Um, Maybe a couple of administrative remarks before we start. So I asked this about Thursday versus Friday. It seems like enough people have problems with Friday that we'll probably keep it on Thursday because even if some people prefer Friday, Thursday is how it's been scheduled, and there's at least 3 or 4 people who will have a serious problem with Friday. So I don't want to move things and make it impossible for those people to attend. So my inclination is that we will remain on Thursdays for the spring. And at the same time, unless people really have an objection, if people would rather do 5 o'clock than 4:30, if anybody really objects to the time on Thursdays, and send me a message on WhatsApp. If there's enough people who really want to change the time, I'm pretty flexible. I can change the time. But for now, let's assume that we will continue to meet on Thursdays at 4:30 in the spring. And I think we will after today, we have a little break for the holidays, and I think we will resume on January 22nd, but I will send that all out in writing over the next few days. Okay, great. Okay, so what I want to do today is uh, go over the homework, review these concepts with Bayes' law and conditional probability that we talked about last week, and then just we're not going to do a new mathematics topic today, but I want to spend a little bit of time just reviewing, summing up everything that we've done this term, and talking a little bit about, what we want to accomplish in the spring. So the first half of class will be kind of traditional, go over the homework, go over the concepts from probability, but then the second half of the class will be a little different from what we've usually been doing so far. Okay. So, all right. So before we go over the homework, I do want to just recall a few of the concepts that we did last week. So last week, the main topic that we were doing was conditional probability. So we're in a situation where we have two events, X and Y, that are maybe not independent from each other. And the conditional probability, we want to determine the probability that X happens given that we know that Y has happened. This is usually in any kind of science what you're doing is that you observe some evidence and you want to understand what's the probability that the system is in a given state. So, you see a rash, what's the probability that you have a certain disease? Things like that. So you observe something and then you want to know how likely it is that something else is happening based on what you've observed. So, there's a storm today. What's the probability there's going to be a storm tomorrow, right? This is important in weather forecast. Okay, so conditional probability is where all of the interesting applications of probability really lie. Okay, so the notation that we use for this conditional probability is the probability of x given y. Okay, so px bar y means the probability that x happens given that we know that y has happened. Okay? And so the main theorem that we have for this, which is our main tool, is this law of multiplicative probability. So this says that if x and y are two events, then the probability that x and y both succeed, that they both happen, is the probability of y times the probability of x given y, right? Where p of xy is the probability of x succeeding given that y succeeds. And I mean, of course, you can write this as an equation. You can write this as P of x and y equals P of y times P of x given y. And just by rearranging this formula, moving the P of y to the other side, we can see that this also gives us a formula for conditional probability, right? So the probability of x given y is equal to the probability that both x and y happen divided by the probability that y happens. Okay. So this is a law that this is the basic law that we're going to use for conditional probability. We're going to have one more page of laws, and then I want to really go through the homework problems slowly. So I only got one submission for homework problems, and it was correct. But I think these problems for most people were probably a little bit more challenging than some of the other problems that we've had before. So I want to go over them nice and slowly so that everybody understands, how to do them and also, how to teach it if you're teaching probability topic in a senior high school class. Okay? So one more law to recall is this law of total probability, which is used in one of the homework problems also. So the law of total probability states that if an event X depends on an event Y, and Y has n possible outcomes, we're going to call them Y1, Y2, up through Yn, then what is the probability that X happens? The probability that X happens is the probability of Y1 times the probability of X given Y1 plus the probability of y2 times the probability of x given y2, plus so on, all the way up to the probability of yn times the probability of x given yn. And I proved this last time, and I think it's worth just going over that proof again. So I want to recall that this is derived from the law of additive probability, which is that if two events A and B are disjoint, which means that they can't both happen, then the probability that either A or B happens is just the probability of A plus the probability of B. So, for instance, if I roll a die, the probability that I get a 2 or a 5 is the probability that I get a 2 plus the probability that I get a 5, right? Those are two disjoint events. The probability that one of them happens is the sum of the probabilities that either one happens. So let me just recall here the proof of the law of total probability. So this proof over here, well, what is the probability of x? Well, we know that y has n possible outcomes, y1 up through yn, and they're all different outcomes. So the probability that x happens is the probability of x and y1 plus the probability of x and y2 plus so on, and we finish with the probability of x and yn. Okay, right? This is using this law of additive probability, right? The probability that x happens, we know that one of y1, y2 up through yn has to happen. So x happening means that either x and y1 will happen, or x and y2 will happen, or x and y3 will happen, or x and yn will happen, right? Exactly one of those things has to happen because y has only these n possible outcomes. One of them has to happen. And so now we have this decomposition of x into x and y1, x and y2, up through x and yn. And now we use the law of multiplicative probability for each of these cases. So the probability of x and y1 is the probability of y1 times the probability of x given y1. And the probability of x and y2 is the probability of y2 times the probability of x given y2. And so on, the probability of x and yn is the probability of yn times the probability of x given yn. Okay, so this is the entire proof. It's done. And the idea is we should think of the law of total probability uh, we should think of it as as combining, so it combines the laws of additive and multiplicative probability. Okay. The law of total probability is going to combine those laws. Okay, because we use the law of additive probability here, and we use the law of multiplicative probability here. You see, this total probability is the sum that's additive of a bunch of products. That's multiplicative. Okay? So in general, you use here to get just an outright probability, you use conditional probability in order to get that. Okay. Any questions about this? We'll go over the homework in a second, but I want to make sure that these are the underlying principles that we need to understand the homework. Okay. Great. Okay. So let's look at, oh, there's one more law I want to recall before the homework. So the last thing that we did last week was called Bayes' law. So we could state it like this: the probability of x given y is equal to the probability of y given x times the probability of x divided by the probability of y. I find this is hard to memorize, and I don't usually use this formulation very much. Um, what I should say is that this is often used to estimate an underlying hidden condition from observations, so estimate the probability of some underlying hidden condition holding. And usually, what's a more effective computational method is when x and y each have a small number of possible outcomes, then we like to calculate this p of x given y using the box method, right? And what we do is we take the probabilities of all possible outcomes and we record them in a box. So we're gonna have this method for one of our homework questions. And then, in fact, we actually just used the law of multiplicative probability. We're going to calculate that p of x given y is equal to p of x and y divided by p of y. And we should note that this is the same as Bayes' law, right? Because this expression in the numerator right here, this is equal to the probability of x and y by the law of multiplicative probability. Okay. Okay, so it really is using Bayes' law, but it's a little bit easier to just think of this as, using the law of multiplicative probability. If you want, p of x given y is the probability of x and y divided by the probability of y. Okay? So these are all of the techniques that we're going to need to use on the homework. We're going to need law of total probability, law of multiplicative probability, and Bayes' law, which is really just a reformulation of the law of multiplicative probability. Okay, and then for at least one of the questions, we're going to end up using the box method. I should say, for the law of total probability, sometimes here, this is also called, we saw an example of this, and maybe we'll do it this way. This is also sometimes called the tree method. Maybe I won't go over the tree method. We'll just see how it works in the course of the homework assignments. Okay. All right. So any questions on any of these laws here? Okay. All right. So if there's no questions, let's move on. Sorry, I froze here. Okay, if there's no questions, let's move on. Okay, so homework exercise one. Suppose that a bag has two blue marbles and three red marbles. I draw two marbles out of the bag. I should say this is without replacement. Okay. Two marbles out of the bag without replacement. So determine the probability that the second marble is blue as follows. So we're going to do the same problem two different ways. So we should get the same answer both ways. So the first one is using the law of total probability. So what are our two cases? We could have that the first marble drawn is red, or we could have that the first marble drawn is blue. And then the second one is, now that we've solved this answer using the previous part, can we think of an easier way to obtain this answer? So in this case, let's just do A on this page. So we have the event X is second marble is blue. Is blue, right? And then the event Y is drawing the marble. So we have Y1 is going to be the event first marble is red. And the event Y2 is first marble is blue. And then the law of total probability, which I'm just going to abbreviate LOTP, that's law of total probability. This says that the probability of X, which is what we want, is equal to the probability of Y1 times the probability of X given Y1 plus the probability of Y2 times the probability of X given Y2. Okay. So let's just evaluate this up here. So what is the probability of y1 so that the first marble is red, and then what's the probability that the second marble is blue given that the first marble is red? So who wants to calculate what these probabilities here are? I know at least Armstrong did this correctly in the homework.
Yes,
Yes.
yes,
Hello? Princeton?
yes, Jason.
Yep.
Yeah, I think what will have to first you to know the total number.
Oh, sorry, I'm not getting you so clearly. It's a little distorted.
Hello?
Oh,
Hello,
much
Bruce?
better. Much better. Yes.
Yes. I think what we have to do here is to know the total marble that we are dealing with. So
Hmm.
some will have two blue marbles and three red, so we add the both, we give us five.
Right. Hmm. Yes, we need the total marbles. Certainly, yes. So we've got five marbles. So let's just focus on these individual quantities. So what's the probability of y1? So we've got five marbles, and y1 is this event, first marble is red, right? So what's the probability that the first marble is red if we've got five marbles? So okay, so Princeton, that's the correct answer. So let's write it down using this method. So what is this probability of y1 that the first marble is red?
So can we say first red is three or five?
Mm-hmm. Yep. So 3/5. So now we need what's the probability that the second marble is blue given that the first marble is red, right? So we've taken one red marble, so now what we're left with is two blues and two reds for four total. So what's the probability that the second marble is going to be blue if what we're left with is two blues and two reds? So I'll
One
put
or
these.
five?
Let's be a little careful, right? So we want to know, right? We're looking at the probability of x given y1. So
Oh, okay.
probability the second marble is blue given that the first marble is red. So remember, this is without replacement. So we assume we've taken a red marble. So what's left is two blues and two reds in the bag. So if I have the bag with two blues and two reds, now I'm going to pick the second marble. What's the probability that that second marble is blue? So I got two reds and two blues in the bag. What's the probability that I pick a blue marble? That's this conditional probability over here. Yep. Enoch? Sorry, it's not getting you. It's getting distorted.
Yeah, Dada Obus.
Yes, yes, Princeton.
So taking that the probability of the blue marble will be equal to 1/4.
So we should be careful. There's two blue marbles in the bag,
Because
right? So there's four total.
yeah, the full. Total is full.
Right. So total is four. And so what's the chance? How
So
many
it's two,
successes? How many give us a blue?
so it's 2/4,
Exactly. Right. So 2/4 is what we get. That's this
which
conditional
which will be
probability.
equivalent to 1/2.
Exactly. Yeah. So let me leave it as 2/4. Enoch, I hear that you're saying something, but I'm not getting anything clearly. It's getting very distorted. Okay. So I can try it, but the sound is not coming through clearly. Okay. All right. So perfect. So right. So the probability that the first marble is red, that's 3/5. The probability that the second marble is blue, given that the first marble is red, is 2 out of 4, right? So now let's try this again, right? So what's the probability? Now, y2 is that the first marble is blue, right? These are the two choices. First marble is red or first marble is blue. So the probability that the first marble is blue is what? We're back to the full bag, right? We've got our 5 marbles. So the probability that the first marble is blue is going to just be, right, we've got 5 marbles. 2 of them are blue.
So
So
two or five.
2 over 5. Yeah, exactly. So it's got to be 2 over 5. Perfect. And now we need to know what is the probability of x given y2. So that means the second marble is blue given that the first marble is blue. So if we take out a blue marble, what's left in the bag? We've got 1 blue marble and
Oh.
3 red marbles. So if we're going to draw another blue marble, what's that probability? We've got 1 blue and 3 reds in the bag. There's still a total of 4 marbles in the bag, right? So the denominator should be 4. But what's the numerator going to be? Well, in this case, we drew a blue already, so there aren't 2 blue marbles left in the bag, right? There's only 1 blue marble left in the bag. So that means that we're only going to have 1 chance in 4 to get the correct blue marble, right? So we're going to get 1 out of 4 over here for the probability. I'll write these numbers down here just to clarify where they're coming from. This is 2/5 here, and this is 1 over 4. Okay? So if you simplify this, simplifying this, this turns out that this is 6/20 plus 2/20, which is equal to 8/20, which is equal to 2/5. Okay. So, okay, so we figured the question out with the law of total probability that and it's just as Princeton wrote um in the um in the chat, is that the odds of getting a blue marble are for the second marble is 2 out of 5. And we did it with this calculation that isn't that bad, but it did require a few steps, and we had to calculate a bunch of different probabilities and add them and multiply them. And in the end, we came up with this answer 2/5. So before we move to part B, first of all, in part A, are there any questions about how we did this calculation for part A?
So that the obvious.
Yep.
Now this problem is telling me that our replacement after we have the total of 5 marbles in this bed, and
Hmm.
and taking one at a time. That means we'll
Hmm.
be leaving with 4, right? That way we have 2 or 4, right?
Right.
Okay.
But if what I took first is a red, then I still have 2 out of 4. If what I took first is a blue, then I'm left with only 1 out of 4. That's why we have a
Yeah.
1 out of 4 here and a 2 out of 4 here.
Okay. Okay.
Okay.
Thank you.
Okay. And so I should mention that we can also do this with the tree method. Let me just remind you what the tree method looks like. It's exactly the same calculation, it's just visualized. We start over here, and then we have a tree, which is here is the first is red, and here is the first is blue, and we'll label the probability of each part of that tree. So it's 2 blues and 3 reds. So the first being red is probability of 3/5. First is blue is a probability of 2/5. And then we go on. We want to know what is the probability that the second is blue. And here we want to know what's the probability that the second is blue. This is what we're trying to figure out. Well, here the probability that the second one is blue is going to be, well, given that the first one is red, we've got two blues out of four, so it's two out of four. Here, given that the first one is blue, we have one blue out of four, so it's one out of four. And then we have the total probability, so the probability that the second is blue. With the tree method, all that we're doing is we go along each branch of the tree and multiply all the probabilities together, and then you add up over all the branches. So it's just exactly the same calculation, 3/5 times 2 out of 4 plus 2/5 times 1 out of 4. Okay, so really same thing, okay? And this again will come out to be 2/5. It's basically just the same calculation, just visualized in a tree. Okay. Okay, but it's exactly the same calculation. Okay, so let me just go back to the previous slide. Um, okay, so that's part A. So the probability is 2/5. So the question for B is, we know this answer is 2/5. This 2/5 is a little suspicious looking. It looks like maybe we should have been able to answer the question without doing such a complicated calculation because the final answer is so simple and it's really related to what we have. So, is there a way to reason why this answer should be 2/5 without using the law of total probability at all? So, is there a way to just know, just from looking at the problem, that the answer has to be 2/5? Let's maybe spend 1 minute thinking about it. And then, if somebody has an idea, can hear about the idea, or if not, I can tell you.
So, Dr. Obus,
Yes, Princeton.
so looking at this problem, the probability of choosing the red, which will be our replacement will be our or over,
Hmm.
our, our plus the probability of blue getting a blue. So it'll be our plus B.
Hmm. Or really, right. So for the blue, it would be B over R plus B, right? Yeah, so that's correct. So, right. So here's a question, right? So, and a question that we already answered, right? What is the probability that the first marble is blue, right? The question says, what's the probability that the second marble is blue? But we could ask a similar question. We could say, what's the probability that the first marble is blue? That's much easier to calculate, right? So the probability that the first marble is blue, that's Y2. We did that already, right? The probability that the first marble is blue is 2/5, right? Look at that 2/5. That's exactly the same as the 2/5 that we got for our final answer, right? So what's the argument here? It's much easier to just calculate what's the probability that the first marble is blue. But I want to claim that the probability that the second marble is blue has to be the same as the probability that the first marble is blue. Because I'm randomly picking marbles out of a bag. Why would any one of them be any more likely to be blue than any other one? Right? If I pick marbles out of a bag, a first, a second, a third, a fourth, a fifth, and I don't know anything about what I've picked already, each individual marble has just as much chance of being blue as any other one, right? I mean, if I'm going to pick five marbles out of a bag and hand them to five people and nobody gets to look at their marble, it's not like the first person is more likely to get a blue marble than the second person, or that okay, thanks, Armstrong. Thanks for letting me know. Or that the second person is any more likely than a third person or anything like that. Everybody's equally likely to have a blue marble. And so, what that tells us is just from kind of pure thought, we're not using any mathematical laws, but just from symmetry, the probability that the second marble is blue has to be exactly the same as the probability that the first marble is blue. So the easier way to obtain this answer is to just say, well, I'm going to calculate the probability that the first marble is blue. Whatever that is has to be the same as the probability that the second marble is blue. But calculating the probability that the first marble is blue is much easier because it's just literally, okay, we've got two blues and three reds. What's the probability of blue? Okay, so let me write this down. I'll put it on another page. So this is to do part B. So what is the probability, or maybe I won't say what is. Let me change that. Maybe I'll say by symmetry, the probability that the first marble is blue equals the probability that the second marble is blue. Right? There's no reason in the absence of any other information, there's no reason why one of them should be any more likely to be blue than the other one. So so can so we can just calculate the first probability, which is what's the first probability? Well, we have five marbles and two of them are blue. So it's two blue ones over the total number of marbles, which is two plus three, and that's 2/5. Okay, so the law of total probability gives you a correct solution. It gives you 2/5. But using a little bit of reasoning and symmetry, you get an easier solution, which is just, oh, well, the second one is kind of irrelevant. I may as well just calculate the first one. It's the same probability. And when I do that, I get 2/5 in a much easier way than doing the whole problem. Okay, any questions on this? Okay. All right. So if there's no questions on this, let's move on to the next let's move on to the next homework question. Okay. Okay. Let me get my Zoom. Okay. Great. Okay, so homework exercise 2. So three balls marked 1, 2, and 3 are placed in a bag. One ball is drawn, the number is recorded, and then it is placed back in the bag. The process is repeated two more times for a total of three balls. So the sum of the three numbers, so I'm telling you that the sum of the three numbers drawn is 6. And the question is, what is the probability that the ball numbered 2 was drawn all three times? So let's again write what this means, right? So let's say that x is equal to x is the probability that 2 is drawn all three times, and let's let y be equal to the probability that sum of the three numbers drawn is 6. Okay. And what we're trying to do is we're trying to calculate the probability of x given y. Okay. Okay, so there's a couple of different ways to do this. Uh, One way is to kind of like count all the outcomes, but let's try to do this using exactly one of our laws. So we're trying to calculate a conditional probability. So usually a good way to do that is to relate it to a multiplicative probability, right? So we're going to use the law that we have from the beginning that P of x given y is equal to P of x and y divided by P of y. Okay, so we want to know what's the probability, and this law is nice because it doesn't require anything about independence. We don't need to know anything about independence. Okay? So we need to calculate these two probabilities. What's the probability that the sum of the three numbers is drawn is 6 and that a 2 is drawn all three times, divided by just what is the overall probability that the sum of the three numbers drawn is 6. And one thing that we can observe actually is that if if x is true, then y is certainly true, right? If 2 is drawn all three times, then the sum of the three numbers drawn is 6, right? So that means the probability of x and y is just the same thing as the probability of x, right? Because once x is true, you know that y is automatically true. So another way that you can write it in this problem is that this is literally just p of x over p of y. Okay? So to actually answer the question, we just need to know what is the probability of x and then divided by what is the probability of y. Okay, and to calculate each of these probabilities, we could do some kind of combinatorics, right? Remember, the probability is deeply closely related to combinatorics. Okay, so so let's try to calculate p of x. I'll just put this up here. Okay, so P of X, we need to know we're drawing a ball out of a bag. There's three balls in the bag, and we want to know what is the probability that every single time we draw a ball, it's 2. So what's that going to be?
So I think we are multiplying the 2 by the 3
Hmm.
to give
Well,
us 6.
well, we're not going to multiply the 2 by the 3, right? But we're making 3 picks, and in each pick, we have a 1 in 3 chance of getting the 2, right? Because 2 is one of the 3 balls. So these are independent, right? Because we're doing it with replacement. We're putting the ball back in the bag each time. So what's the probability that each of the 3 times we draw a ball, it's a 2? How do we calculate that? Well, what's the probability that the first ball that we draw is a 2? Right? So there's 3 balls in the bag. What's the probability that the first ball that we pick is a 2?
Yes,
Yeah.
Joe.
Hello. Yep. Armstrong?
Hello.
Hello. Yes.
Come again.
Yeah.
Yeah,
I said hello. Yep.
come again.
I asked, so what is the probability
So
that
what's the question?
we draw? So what's the probability that we draw? We're trying to find the probability of X so that all 3 balls that we pick are the number 2. Is the law.
Let me see. Then we have
Yeah.
1/7.
Okay, well, 1/7 is going to be the final
I'm
answer, but
so
I'm trying to do this in a few steps. So we've shown that it's going to be P of X divided by P of Y.
yeah, we
Yeah.
can do. Hello.
Hello, yes?
Yeah, we have I think 6 different ways to arrange the number 1, 2, 3 to get
Hmm.
the probability of getting 2.
Right.
Then we have getting 2 out of the 7.
Hmm. Yeah, so this is going to work. But I want to show how this is approached in a bit of a different way, right? So exactly. So there's one way to get 2 all 3 times, right? So the probability of that happening is, well, to get a 2 in a given draw is a probability of 1 out of 3, right? To do that 3 times, these are 3 independent draws. So we're going to have 1 out of 3 times 1 out of 3 times 1 out of 3, right? That's the probability of getting a 2 all 3 times. So that's going to be 1 out of 27. Okay. So, or another way of thinking about it is that there's 27 different ways to draw these balls because there's 3, 3, and 3, and there's exactly one way of getting a 2 all 3 times. So you have to get 2, 2, 2. Okay, so what Armstrong is doing is calculating this P of y. Okay, so we want to know what's the probability that the sum of the 3 numbers drawn is a 6. So we can think of this with the standard way that you do probability, which is number of successes over the total number of outcomes. Okay? And so, well, the total number of outcomes, we know that you're picking 3 balls, 1 out of 3 balls, and you're doing it 3 times. So the total number of outcomes is just 3 times 3 times 3. That's going to be this 27 again. And what's the total number of successes? Well, what Armstrong said is, how can you get the sum of these 3 numbers to be a 6 if you're picking 3 numbers out of 1, 2, and 3? Well, one way of doing it is getting a 2, a 2, and a 2. Another way of doing it is getting a 1, a 2, and a 3. But the 1, the 2, and the 3 can come in any order, right? So you can get 1, 2, 3, or 1, 3, 2, or 2, 1, 3, or whatever. There's lots of different ways of getting a 1, a 2, and a 3. So what's the total number of successes? We have a 1 over here. This corresponds to, 2, 2, 2. And then you have 1, 2, and 3 that can go in any order. So how many ways do we have of permuting 3 different things? Well, that answer is what we called 3p3, or 3 factorial. So this 3 times 3 times 3 is 27. This 1 plus 3p3 is 1 plus 6, which is equal to 7. Okay, and what I should say is that what is this 6 over here count? This thing over here counts, 1, 2, 3 in some order. Apologies for the print being small. Zoom in on it. That just says it counts 1, 2, 3 in some order over here. Okay, the number of ways of getting 1, 2, 3 in some order is exactly 3p3. It's the number of ways of permuting 3 things. 3p3, if you recall, is just 3 factorial over 0 factorial. It's equal to 6. It's 3 factorial. So we end up with 1 plus 6 equals 7 successes, and you can write them out explicitly if you want. You have 2, 2, 2, and then you have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. Okay, so the numbers are small enough that you can just write them all out if you want. Okay, so that's going to give you 7, and the total number of outcomes is 27, because each pick you have 3 choices, and they're independent. So you get 3 times 3 times 3. So the probability of x is 1 over 27. The probability of y is 7 over 27. The probability that we're looking for is p of x divided by p of y. So what we're getting, that this p of x divided by p of y, we see that this is 1/27th divided by 7/27ths, and this simplifies to 1 over 7, which is the final answer. Okay. And so, I mean, of course, you can say, oh, just count the successes, count the number of total ways. That is another way to do this. I wanted to link this to the law of probability. You could also just directly say, given that the sum of the 3 numbers drawn is 6, there's 7 ways of doing that. That's this count here. One of those ways is having the ball number 2 drawn all 3 times. So the probability that the 2 is drawn all 3 times, given that the sum of the 3 numbers drawn is 6, is exactly 1 divided by 7. There's 1 success divided by 7 total outcomes. Okay, this way of doing it is a little bit longer, but it illustrates how this law of multiplicative probability can be used. This is a standard thing about probability and combinatorics questions is that there's often more than one way to do them. There's usually more than one correct way to do them. You have a few different laws and a few different principles, and sometimes multiple choices of laws and principles will end up giving you the right answer. All right, so are there any questions about this problem? Okay. All right, no questions on this. Let's go to the third exercise. Okay, so third exercise, it's estimated that 50% of emails are spam. A software program claims that it can detect 99% of spam emails and that the probability of a false positive, by which we mean a normal email that's classified as spam, is 5%. Okay? So if an email is detected as spam, what is the probability that it is actually spam? So this is a classic box method kind of problem. Again, you can call it Bayes' law, but I find it much easier to just think of this as a box method. Right? So there's not that many choices, right? So we have our box here. It's just a 2 by 2 box. And then here we have the two choices for the email is it spam or not spam? And then we also have two choices for how it's detected, right? So I should say, flagged as spam and not flagged as spam. Okay. So, and what we're going to know is, and so what are we actually trying to figure out? So often in these box problems, you don't actually need to fill out the whole box. So we're saying that if an email is detected as spam, what is the probability that it is actually spam? So since we're doing that, given that the email is flagged as spam, it turns out that we really only need to calculate the two probabilities in the top row of the box. Okay. We can calculate them all just for practice, but we'll see that in the final calculation, it's only these two entries that get used. Okay, so let's see. So we have spam. What is the probability that an email is flagged as spam, that it is spam and it is flagged as spam? How do we calculate that? So what probability do we put in this box over here? Yes.
0.99.
0.99. So yes, so 0.99. I'm going to write that actually over here as the second thing. So 0.99 times what? So what is 0.99? That represents if an email is spam, the chance that it will be detected
Okay,
is
I
99.
have 0.5.
0.5, exactly. Right? So we're going to have 0.5 times 0.99, right? Because this is that it's spam and flagged as spam. So that's the same thing as probability that it is spam, that's 0.5, times the probability that it's flagged as spam, given that it is spam. And that's what this 99% is. It says if the email is spam, then it's detected as spam 99% of the time. So this is exactly what we get. So we get 0.5 times 0.99. That's what we get in this box over here. Okay. All right. So what about this box over here? We want to know what's the probability that an email is flagged as spam, but it's not spam. Yes, Armstrong?
Okay.
Princeton.
We have 0.05%.
Right. So 0.5.
0.05.
times 0.05. Exactly. Right? Because what do we have over here? We have that the fact that the chance that the email is not spam is still 50%. But now, what's the chance that it would be flagged as spam, even if it's not spam? Well, that's 5%. Okay? So the fact that it's not spam, but it is a false positive, would be 0.5 times 0.05. Now, in reality, to solve this problem, these are the only two probabilities that we need. But just for practice, let's fill in these other two boxes. We don't really need them to solve the problem. So if we want a spam email that's not flagged as spam, that would be a spam email, so it's still zero point 0.5, but that it's not flagged as spam means, well, 99% of them will get flagged as spam, so the chance that it's not flagged as spam is only 1%. So that's going to be 0 0.5 times 0 0.1. Is that it's not actually, sorry, not 0 0.1, 0 0.01, only 1%. And then what is the chance that an email is not spam and that it's not flagged as spam? Well, not spam is 0 0.5. And then if it's not spam, what's the chance that it's not flagged as spam? Well, if it's not spam, we know that if it's the chance that it is flagged as spam is 5%. So the chance that it's not flagged as spam is the rest of it. So it's 95%. So this is going to be times 0.95. Okay. So these are all, using the law of multiplicative probability. We're saying what is the chance that it's spam and what is the chance that it's flagged a certain way given that it is or is not spam. So these all use the law of multiplicative probability. Okay. But now in reality, what this problem is telling us is it's saying that an email is detected as spam. So in fact, to calculate the probability that we want, we're only going to need to use this top row. Okay. So what do we need to calculate? We're trying to calculate the probability of spam given that it's detected as spam. Okay? And we know from this law of total or multiplicative probability, this is the probability that it's spam and detected divided by the probability that it is detected. Right? Okay, is it 4.95%? I think it should be a little bit higher than that. Okay, so we tried to fill out this, but maybe after we do the problem, we'll talk a little bit more about how to fill out the full box. Okay. So, okay, well, the probability that it's spam and detected is this upper right-hand corner. So Princeton, I think that's what you mean. That spam and detected is exactly this upper right-hand corner. So we have 0.5 times 0.99. That's the probability that it's both spam and it's detected as spam. So now what's just in general the probability that it's detected as spam? Well, that accounts for the probability in both of these boxes, right? Both of these, if it's flagged as spam, it could be spam, or it could be not spam. Exactly. Not spam is 0.025, right? So it could be the first one, or it could be the second one. Okay, this is actually the law of total probability. What's the probability that you're flagged as spam? It's that you are spam and you're flagged as spam given that you're spam, plus the probability that you're not spam and that you're flagged as spam given that you're not spam. So in this case, we have to add these two. So I'm just going to keep it like this, 0.5 times 0.99 plus 0.5 times 0.05. And now we can write this all down. Yeah, so if you want to write this, this is 0.495 divided by 0.495 plus 0.025. And this turns out to be, let me just do this on the calculator. So 0.495 divided by 0.495 plus 0.025. So this turns out to be roughly 95.2%. Okay. Okay, so this is saying that if it goes to your spam folder, then it has a 95.2% chance of being spam. But that still means that it has a 4.8% chance of not being spam. So you should probably look in your spam folder every once in a while to make sure that nothing too important has ended up there. Okay, any questions about how we did this here? Okay. So this comes out to be 92%, 95.2%. And again, it's good to practice filling in the whole box, but since it's asking about just what happens when an email is flagged as spam, that means that you really only need to do the part of the box that corresponds to when this is flagged as spam. Okay. Okay, so this turns out to be 95.2%. And then maybe I'll just do I'll do this box in a little bit more detail just to go over how we did it. So how did we calculate I'll do this in another box. So just I'll say in more detail. Let's compute the probability of, so what's that box? It's going to be not spam and not flagged as spam. So the probability of not spam and not flagged as spam. Okay. Well, by the law of multiplicative probability, this is what's the probability of both things happening? This is P probability that it's not flagged as spam. Or let me say, actually, it's the probability that it's not spam times the probability that it's not flagged given that it's not spam. Okay, not spam times the probability that it's not flagged given that it's not spam. So the probability that it's not spam, we go to our original data. It says estimated that 50% of emails are spam. Okay, so that means 50% of emails are not spam. So just overall, the probability that an email is not spam is going to be 50% or 0.5, right? 50%. Okay. And now over here, what's the probability that given that it's not spam, that it's not flagged? Well, given that it's not spam, we say the problem says the probability of a false positive. So it's saying if an email is spam, if an email is email is detected. What do I want to say? I want to say that it's not flagged, given that it's not spam, right? So an email that is not spam. Why am I getting confused here? Oh, right. Yes. Okay. That's right. So if it's not spam, that means it's a normal email. So the chance that it's classified as spam is 5%, which means the chance that it's not classified as spam is 95%, right? 5% are spam. That means 95% have to not be spam. So the chance that it's not flagged, given that it's not spam, this is going to be exactly 0.95 or 95%. Okay. So the final probability is exactly 0.5 times 0.95, or if you want to write it all out, this is 0.475. Okay. Okay, so this is the procedure which we use to fill in each box. Okay, so each box is an and, right? This is spam and flagged, not spam and flagged. spam and not flagged, not spam and not flagged. So it's all of these ands. And to calculate any of these ands in probability, you're always going to be using the law of multiplicative probability. Okay, and so this is just one example for not spam and not flagged. You say the probability that it's not spam. Let me actually do this. I think this will make it a little bigger on the screen. Okay, probability that it's not spam times the probability that it's not flagged given that it's not spam. This is how we use law of multiplicative probability, and we can use this to figure out every box. And then in the end, to do the actual problem, you don't need every box. You only need two of the boxes. Okay. So I'm completely fine to have taken an hour going over these problems because I think these are tricky problems. They're important to really understand well. They're not just here's a formula, plug it in. There's a few different rules that you have to figure out what to do. But yeah, so I wanted to make sure that this made sense. This is clear to everyone. So, are there any further questions about any aspect of this problem? Okay. And again, I'll send this out. So if you want to look over the document again, then you'll have some time if you need to spend a little more time on it. Okay, so we don't have that much more time left today, only 25 minutes, but that's actually good because we're not really doing new math today. I want to kind of sum up and review what we've done and where we're going. Okay, so where are we now? So what have we done this semester? Right, so this semester we've studied four topics from the high school curriculum. There's certainly not the entire curriculum, but we've picked four topics. There's kind of a reason I picked these four topics. So we started with exponentials and logarithms. We moved on to word problems. I think actually we did geometry first, and then we did word problems, and then we did combinatorics and probability, which are, I guess, combinatorics and probability are two different topics, but they really go together. If you study one, you should study the other one together with it. Same thing with exponentials and logarithms. If you're studying exponentials, you want to study logarithms with it. And we didn't take exactly the same approach to every topic. We took different but overlapping approaches to each of the different topics. So let me just quickly recall, because we had this whole semester, let's recall what we did topic by topic, especially if some people missed a class or had a bad network for a lot of a class. So what do we do topic by topic? So with exponentials and logarithms, what did we do? Well, after recalling the basic laws of exponentials and logarithms, we discussed types of questions that teachers should be prepared to answer. And this included questions involving less straightforward numbers, being able to solve algebraic equations using logarithms, questions where it's not immediately clear which rule of logarithms or exponentials should be applied, and also questions involving applications of logarithms to real-world phenomena. And these tended to take the form of word problems. So we had word problems about decibel level in sound and pH in chemistry and radioactive decay or exponential growth. And then we also did the Richter scale. So various real-world problems that involve logarithms. So in addition, we asked you to come up with and solve some of your own problems, demonstrating at least one of the above ideas. And one common thread, regardless of what type of question we were looking at, is that we had a small list of rules, right? And usually what students find is that if you have a problem and you're told to apply a rule, they can usually do that pretty well. Okay, once they learn the rules, you'll be like, okay, apply the additive law of logarithms to show that, the logarithm to base, 10 of 1000 is equal to the logarithm base 10 of 10 plus the logarithm base 10 of 100. Like, if you tell them exactly what to do, they can do it. But one of the harder things is figuring out when you're not told exactly what to do, or it's not clear from context what to do. Okay? So common thread is you have a small set of rules. The challenge is not really applying the rules. The challenge is figuring out what rule to apply, translating your problem into something that involves rules that you know how to apply. Okay, so this is what we did with exponentials and logarithms. Okay. Next unit, we had geometry. So geometry, of course, is a giant subject. There's lots and lots of geometry. We only did 2 sessions on it, so we only had a very small part of geometry. So what did we actually talk about? We talked about mensuration. This was cataloging various formulas for computing 1 and 2 and 3-dimensional quantities. 1-dimensional quantities were length and perimeter and circumference. 2 dimensions was area and surface area, and 3 dimensions was volume. And we showed that if you have a given dimension, even formulas that don't look the same, like the area of a circle versus the surface area of a pyramid, these are very different formulas, but we did show that these formulas, if you fix a dimension, all formulas in that dimension have something in common. That was this scaling behavior that we talked about. So what did we also do? We also reviewed some basic facts about triangles, and then we discussed about how lots of problems, at least involving polygons in plane geometry, can be reduced to problems about triangles. If you have a quadrilateral or a pentagon or a hexagon, you can usually divide it up into triangles and somehow make the problem about triangle. In particular, what did we derive? We derived area formulas for polygons with an inscribed circle, and we solved several area problems involving quadrilaterals. And in all of these cases, we solved the problem by reducing it to the case of triangles, and only depending on area formulas for triangles, of which there are a lot, right? I mean, you have 1/2 base times height, you have 1/2 AB times C, you have Hero's formula. There's a number of different area formulas for triangles. But you can use whichever one is more convenient. But and in particular, it's hard to memorize area formulas for polygons that are more complicated than triangles. So the only way I really know how to do these problems is to reduce them to the case of triangles. Okay, so this is what we did in geometry. Okay, what about word problems? That was the next unit. So we use this Keska method, key, equation, solution, check, answer. This method of solving word problems. And our goal was to be able to solve any word problem using this method. Word problems can be very different from each other. They can involve, at the most basic case, a linear equation in one variable, a single linear equation in one variable. We then solved problems that gave rise to quadratic equations, many of which involve more than one variable. So these were some of these more complicated word problems that involved, planes with wind going back and forth, or problems about swimming or boats that also took into account current or runners at different speeds. A lot of these types of questions ultimately give rise to quadratic equations. Then what do? We also solved some problems that involved inequalities rather than equations. And again, we asked you to come up with and solve some of your own word problems using Keska. And what tied everything together? Well, despite the fact that some of the problems required more effort to set up than others, we were able to ultimately apply Keska to them all. And what was the hard part? In almost all these questions, the hard part was setting this up. Okay, the K and the E, right? Making carefully saying, what are my variables and what do they mean? If I don't want to just write X and Y, I need to write, what does X mean? What is Y, right? If I'm going to write down an equation, I'd better know what the variables represent. So you have to do the key very carefully. And then actually setting up the equation or the equations is, I think, the skill that your students are going to have the most trouble with, right? They have to translate from a paragraph from words into mathematical equations. So that's, I think, the main skill you have to work on with word problems. Because again, once your students have the correct equation with the correct variables and know what they're trying to solve for, often actually solving the equations is something that they can do a little bit better, right? I'm almost certain that more of your students can accurately solve an equation that's given to them than the number of students that can accurately set up the equation given a complicated word problem. And once you've set up the equation wrong, then it doesn't matter how well you solve it, you're not going to get the right answer. So, especially with Keska, I think you really want to focus on getting things set up correctly, the key and the equation. Okay, once you have that, then you can solve. Okay, so it's an overall method that works basically for any word problem, even if the equations that you get will look a little different. Okay, so this is what we did for word problems. Then we had a unit on combinatorics and probability. We started with combinatorics. That then went to probability. What did we do in combinatorics? We talked about the multiplicative principle for independent events. This, how many five-digit numbers start with an 8, things like that. You can calculate this using, you split up the event into small pieces and you multiply the number of choices that you have at each point. This was kind of the fundamental idea of combinatorics. We showed how just from this multiplicative principle, you can solve lots of combinatorics problems. And in particular, you can calculate permutations. You can calculate how many ways there are of picking, R elements out of n, out of a set of n, where order matters, right? So this idea of uh yeah so yeah so this idea of how to how to do permutations was based on this multiplicative principle. Sorry, 1 second. Okay. Um, Good. Okay, so this is the first thing. So then we said, well, the multiplicative principle for independent events doesn't it gets you pretty far, but it doesn't let you do everything. So, it requires sometimes you need to be able to count non-independent events. And we had certain ways of doing this. We had two principles. We had this cases, which we also called the additive principle in combinatorics. And then we also had this counting the wrong thing. Sometimes if you want to count something, what you do instead is you count some bigger set and then you throw away all the ones that don't work. So you want to count numbers where a letter is where you want to count numbers that have two of the same digit. You count numbers that don't have any of the same digit. That's easier to count, and then you subtract them from the total count of numbers. Okay. Sorry. 1 minute. I need a 1 minute break. I'll be right back. Hi. Good. Everything's good. Okay. Well, good. Uh, yeah. Okay. So this was what we did in combinatorics. So then we went to probability, and the first principle we discussed was this law of multiplicative probability for independent events, which is the exact analog of the multiplicative principle in combinatorics. But then the juicier probability problems, the more difficult ones, generally don't only involve independent events. So we had to talk about conditional probability, where the probability of an event X depends on the probability of an event Y. And then we did non-independent probability. And that meant that we have the law of multiplicative probability, the law of additive probability, the law of total probability, and then this Bayes' law at the end, or the box method. And basically, just about everything that we did in probability, either you can reduce it directly to combinatorics, where you're counting the number of successes divided by the number of total possibilities. That would be reducing to combinatorics. Or you reduce it to the law of multiplicative probability. I don't want to say for independent events. Let me erase that. Let me just say the law of multiplicative probability or the law of additive probability. Okay? So basically, by combining those laws, you can solve basically any probability question that you're going to see, certainly at the high school level. So even these complicated box method type questions, in the end, you're just calculating a bunch of probabilities using the law of multiplicative probability, and then you're dividing, to figure out a conditional probability, you're also using the law of multiplicative probability to do that. Okay? So we have these, again, combinatorics and probability. It's a little tricky because you have 6 or 7 things that you need to remember. You need to remember formulas for permutations and combinations. You need to remember a few different probability laws. You need to remember these basic principles of combinatorics. But if you can memorize all of those things, then there's not that many different ways that you need to be able to apply them. Okay. So, okay. What did all of these approaches have in common? Well, they're not exactly the same. But I would say one thing that all of the approaches have in common is trying to reduce a large field of study to a few principles to memorize. Okay, so trying to make it so that there's not that much that you have to memorize. There's a few principles or a few formulas that you have to memorize, but there isn't that much that you need to know. So then a second thing that they had in common was lots of different problems of increasing difficulty that use the same principles. Okay, so for example, if we want to go to word problems, we have Casca. There's only Casca's even easier. It's really one principle. There's not even, three principles that you have to memorize. It's just one. But we did a lot of different word problems, and we saw how they can really get harder and harder and harder, even though they're still based on the same principle. Okay? So lots of different problems of increasing difficulty using the same principles. And then number three, how difficult did the questions get? I would say difficulty, because this is a workshop for teachers, not a workshop for students. And so I would say that the difficulty tops out, it increases, so it tops out at a level somewhat more difficult than what we expect an average or even a good student, if we expect an average or even a somewhat above average student to be able to solve. Okay, my guess is that the average student in a class is probably not going to get one of these box problems, complicated probability questions right. Um, some students will, your better students maybe will, but most students probably will not. But as a teacher, it's important to be able to solve problems that are more difficult than what the average student can solve, right? And it helps if you have questions. It also helps if what you're teaching is a little bit easier than what you can actually do. Then it allows you as a teacher to really be focusing on pedagogy instead of on like, oh, do I really understand how to do this problem or not? Okay, so I think it's important you have your few principles. You have um, one second. You have a few principles. You have problems of increasing difficulty, and you don't want to stop the difficulty too low. You want to go up to a level that really is, if you can handle that, then you're going to be able to handle anything that a student's going to ask you, anything that's going to come up on WAS or something like that. Okay. So this is something that even though these were a lot of different subjects, these are some principles that when I'm trying to design a workshop on a topic that I try to keep in mind. Okay. So so maybe we'll talk about this more on the chat then today because we're almost out of time. So what are topics for next semester? So what are other topics in the curriculum that we should try to design a mini workshop for? So a mini workshop, I think of it kind of like what we had this semester, which was, for each of our topics, we spent about 2 to 4 sessions on them. I think we spent the most on combinatorics and probability. That was 4. Geometry maybe only had two, but something like that. A few sessions, call it a mini workshop. So the question would be, what types of topics should we try to design a mini workshop for? And what I'd like to try to do next semester is to do this as a bit of a collaborative design. Okay. So during class, I know it's hard to collaborate because people are in loud environments or the network's not so good. So I think what's better is to try to be able to send messages on WhatsApp during the week where people brainstorm their ideas for what kinds of topics we should try to design some mini workshops for. So again, maybe, over the next month, participants can send ideas to the WhatsApp chat. Okay. So over the next month, participants can send ideas to the WhatsApp chat. And then also for next semester, depending on popular demand, I'd like to get us thinking about how to design these workshops. But also, if we have some time, it might be good to do some training that's directly related to kinds of exams that your students might have to take. So, directly for coaching students for exams for the WAS, for the WITS math competition, etc. And for the WAS, what I'm going to need, I don't know if we have any administrators still here on the call. I think we have AB. I should ask Deborah for this, but I need to see. So this is a question from me. So can I get copies of old math WAS exams? Okay, so it's hard for me to get to prepare and try to design a workshop for this if I haven't really seen the exams. So if anybody's able to get me some copies of old Math WAS exams, it would be good for me to look over them during the break so I can see, what the questions are like, what tends to be on them. Okay. Um, so we can do some training directly for that, and for WITS math competition, of which some of the participants here are coaches, we can go over some of the types of questions they like to ask on that. Um, so just to recall, last thing, references for this semester, at least from this book, The Art of Problem Solving, Volume 1 that I sent. For exponentials and logarithms, Chapter 1 is a good reference. For geometry of triangles and quadrilaterals, Chapters 11 and 12 are a good reference. For word problems, Chapters 3 and 6 are a good reference. And for combinatorics and probability, this all came from Chapters 25 and 26. Of course, there are lots of other chapters. Other chapters to read for your own enjoyment if you want. You can read these all for your own enjoyment and training if you want. And okay, so as always, thank you for your attention. We'll resume. I think I worked out the schedule actually. So we're going to resume in late January. I think we're going to stay on Thursdays based on what everybody has responded. We're going to stay on Thursdays. There's enough people who have built their schedule around Thursdays that I don't want to change. So the essay part is good, but it's really the math. So I don't know if the essay part, if it's not for math, then that's not so useful. What I need is old math WAS. And so
Okay.
first, sorry.
Yeah. Andrew.
Yeah.
Andrew.
Yep.
Hello. I
Hello,
want to
AB.
add Deborah. I want to add Deborah to because Deborah been working on the math
Hmm.
on the wax paper. So I
Okay.
want to ask her if she can get some of the papers for her because most of the students can't keep their papers.
Right.
So we will also ask some of the teachers to see whether they can get some of this the wax paper for us, then we can be able to put it in our calendar too to see where we can start teaching from there.
Okay. That'd be very useful.
Yeah. Okay, thank you.
Okay. You're welcome.
Okay, also thank you. Thank you for the class. Happy Christmas and prosperous New Year for you.
Yes, absolutely. Merry Christmas and Happy New Year. I'm not. I have one more minute. I just want to say one thing before we break. So,
Yeah.
so the first class after of the break is going to be January 22nd.
Yeah,
That's going to be
okay.
our next class. And then I will send syllabus, syllabus and schedule after the new year.
Okay.
Okay, but the first class will be January 22nd. So I'm gonna circle
Okay.
that now. Okay. Great. So thank you very much
Okay.
for
Thank
everybody
you.
for coming and paying attention. And yes, of course, yeah, Merry Christmas, Happy New Year, have a wonderful holiday break, and thank you for sticking with us for the whole semester.
Okay, thank you.
All right, you're welcome. Okay, I'm gonna stop. Oh, and also, if anybody didn't type their name in, last chance to type your name before I stop the recording. Okay, so I'll give one more minute for people to type their name in, and then I'll end the recording. Okay, you're welcome, everybody. Um, have a great New Year. I'm gonna go stop the recording now.